Hello and welcome back. I hope you enjoyed linear regression. So now we will move on to classification, and we will start classification with logistic regression. Okay, and I hope you enjoy that. We will start with the very basics of logistic regression. Hello, so let's get started with logistic regression. Okay, so logistic regression is an algorithm in machine learning to address the classification issues. So let's quickly visit what was classification. So the same problem that we had done, that predicting the future salary of a student from his marks on some semester or maybe the final semester. So we had earlier tried to predict the salary, but now let's say we try to predict whether the student will get placed or not. Okay, so a 1 if the student gets placed and 0. So these are all historical records of students who have been placed, and 0 represents students who have not been placed. So this is now a categorical problem, not a continuous output, but a categorical output. Okay, so then let's see how we could address this issue. So let's say we can plot these marks on a two-dimensional. We have 2 marks, so we can plot this on a two-dimensional plane. So if we plot this, suppose the marks of marks 1 along the x-axis and marks 2 along the y-axis, and I have marked in green those which are 1 and marked in red those which are zeros. So we can see that these are the students who have got placed and these who have not been placed. So what can we do? How can we learn? How can we can easily see? So we can see anything over this region of the plane might be someone who is not getting placed, and anyone over this region is someone who is getting placed if the marks are over this region. Okay. Alternatively, what we can do from what we have already learned, a linear regression. In linear regression, we plot the y against all the x's. So here we have taken a 3-dimensional graph and also have plotted the ones. So you can see this y-axis, or maybe this is the z-axis. Actually, this is the y-axis. Is only between 0 and 1. Okay, so what we can do from our linear regression approach is we can regress over this and we can try to learn a 1 or 0. Like our outputs can be 1 and 0, just as they were the marks in the previous case. So how can we do that? So we used to learn a line in a 3-dimensional space. It would be some sort of a plane. So we learn the equation of this plane and say we try to then our motto is to predict an unknown student. Suppose a student has this marks in one subject and this marks in one subject. So we find that the student meets both the marks meet over here on the marks plane, and we project it on this plane, and if it's somewhere over here, okay, so it's more closer to 0, so the student doesn't get placed. And had it been somewhere over here, which is more closer to 1, we could have said that the student has got placed. So we could very well follow a linear regression approach here and find out whether this works or not. Okay, but isn't it a better approach if we go back to this graph or this representation, and we draw some sort of, we find the equation of this line. Okay, and this line, this is a separated line or a boundary line which separates the marks of the students from this to marks of the students in this region. Okay, and we can say if it's greater than 0, we can put the values which is greater than 0 and it falls in this region, then yeah, it gets placed. Or if it's less than this one, we say it doesn't get placed. Okay, or maybe the reverse. Okay, so now let's see how we can do this approach or maybe this approach. So what we can do, so as you know, like apart from marks, we take a bias term. So some ones over here also, all along this we put some ones. Okay, along one more we add one more column of ones, and we assign 3 weights, W0, W1 and W2, which when multiplied with the corresponding marks gives us either 0 or 1 or something between 0 and 1, from which we can predict that whether the student will get a job or will not get a job. Okay, so we will initialize the weights randomly with 0, 1 and 2, and we'll try to learn some values of the weights through an iterative approach, which will bring us close to these students outputting 1 and these students outputting a 0, which when multiplied with this. And we have learned from our basics of machine learning that we can transpose this and do a dot product with this matrix to learn this, and do a gradient descent, so that this weights, how will this weights adjust? This weights will adjust through an iterative approach of gradient descent. Okay, that was in our linear regression video. But there's one problem. So let's first randomly assign 1, 1 and 0 to these weights and see what happens. What happens is the predicted values becomes these. It's so much different. It's only 1 and 0, and it's different from even the ones as well as the zeros. And so what is our error here? So we have a high error, that is the difference and the square of the difference, and then summing this all up, the squared error, sum of squared error is very high. Okay, so what we can do, we can apply a tweaking here, a mathematical tweaking here. What we can do is we have some sort of a function called the sigmoid function. So what's it's a very interesting function. The sigmoid function keeps the value clipped between 1 and 0. You can see somewhere near 0 it's 0.5, but as we move higher it goes towards 1, and then it straightens, almost straightens, it never goes beyond 1. Similarly, as we go lesser, it also straightens and never goes beyond 0. And within this range, within a small range, it's almost a linear function. Okay, so what we can do, we can apply this function on these values and clip the outputs between 1 and 0. So let's apply the sigmoid function, which is 1 by 1 plus e to the power minus x. We apply this sigmoid function on each of these predicted outputs and clip it between 1 and 0. So now here, so we applied the predicted values and we applied the sigmoid function on the predicted values, and now we see the difference. It's not that much, and now it's 0.55. And now we can have some gradient descent again on some optimization techniques to bring whatever is mismatching, so that we find some weights that this becomes matching and we could find. But there's one more problem here. Not a problem, but it seems that we can make it more perfect or make our algorithm better. Since it's 0 and 1, so what we want to do is, when it's 1 and we predict a 0, we want to penalize and maximize the error. And when it is 0 and we predict 1, in that case also we want to maximize the error. So we have to find this error calculation, which was our sum of squared error. But we may use something else, so that when we can penalize the misclassifications. So there's another beautiful function with which we can do that. So let's see what minus log x does. So minus log x, so let's consider this as when the actual values are 1, that is the actual for this case, and so on. When the actual values are 1, when our predicted values come closer to 1, the minus log x function would be almost closer to 0. Okay, and when it's the actual values are 1, if the predicted values are somewhere near 0, the error increases, and this increases infinitely. Okay, so more and more we are coming closer to 1, the error is less. So using this we can penalize. If we are going to predict 1, if we are trying to predict 1, we can penalize those who are not we can penalize those values which are not predicting 1 in a very high way. And similarly, we have another function, just a rearrangement of this minus log 1 plus x, with which we can penalize for zeros. Like if the actuals are 0 and we are predicting somewhere closer to 1, the error gets higher. Whereas if the actuals are 0 and our prediction is also close to 0, so the penalty is very less. Okay, So somewhere we can combine these two using our actual y values into one function. Okay, and this is what we will use to calculate the error and not this one. Okay, and we will find the gradient of this and try to minimize the error. Okay, so how do we minimize the error? We do the differentiation of this and adjust the weights, the w's, with the values that we get from the gradient using a learning rate that we learned from our linear regression class. So when we differentiate this, we get this is the equation. Okay, so each weight can be reduced by this times the learning rate. That will give us that will help us to learn the logistic regression. And what will happen in that case is we can show it mathematically that if we have three weights w0, w1, w2, and we can reduce the value of this error to 0 by adjusting the weights with this in each iteration, we learn three weights, and those three weights give the equation of this line. Okay, that is, we learn w0, w1 and w2. So we can say this, the equation of this line is w0 plus w1x plus w2y, and whether it's greater than this or less than this, we can assign whether student is 1 or 0, like that. Okay, so it can be mathematically proven that how this equation corresponds to the separation line. Okay, so that's the basic of logistic regression. If you are interested in the proof of how this equation turns out to be the separated line, I can put up a separate video on that. Please leave a note in the comment. Thank you.